A rancher has 200 feet of fencing to enclose two adjacent rectangular corrals. What dimensions should be used so that the enclosed area will be maximized? Okay, so the first thing I'm going to do is try to get a picture. Okay, we got 200 feet of fencing, and we want to make two rectangular pins. They're going to be adjacent to one another. So it looks like our picture could look something like this. Okay, the pins are adjacent to one another. I only need one piece of fencing to form the two pins right here in the middle. And I'm going to want to know what my dimensions are. So we can say this length is X and this length is Y. Okay, notice that I have two pieces that have length X. Okay, and so from that 200 feet, I'm going to need to get those two pieces. Plus, I'm going to need to get three pieces that have length Y. 1, 2, 3. Okay, so I can make an equation that looks like 2x plus 3y equals 200. Okay, and that's going to meet my conditions for the amount of fencing. Okay, we're going to use 200 feet of fence, and I need to get two sides of length x and three sides of length y from that 200 feet of fencing. Okay, my goal here is to maximize the area. The area, total area of this pin is just going to be x times y. So I want to maximize A equals x times y. If I can, I want to try to get, instead of two variables, just one. And that's where I'm going to use the equation that we came up with over here, 2x plus 3y equals 200. I'm going to solve for one of my variables. I think I will solve for x. And so we get 2x equals 200 minus 3y, or x equals 200 minus 3y divided by 2, or x equals 100 minus 3/2 y. So I'm going to take this expression for x and substitute it into my optimization function, the function that I'm trying to maximize. So now I can say that area is equal to 100 minus 3/2 y times y, or 100y minus 3/2 y squared. Okay, and we want to maximize this area. Okay, so in order to figure out where this function might have a maximum, the first thing I'm going to do is take a derivative. We get a prime is equal to 100 minus, if I bring the 2 out front and multiply it by 3/2, we get 3y. Okay, in order to find my critical values, I'm going to set this equal to 0, and we get 100 equals 3y, or y equals 100 over 3. Okay, so potentially this could be a maximum or a minimum at this point. This is a critical value, so I need to verify that it's going to be a maximum or a minimum. There are two ways to do that. We could set up a sign test using the first derivative, or I can use my second derivative test. I'm going to choose to use the second derivative test. So I'm looking at my second derivative, which in this case is just -3. Okay? And so that tells me that this function is concave down. Okay? It's concave down everywhere. Even at our particular critical value, it's concave down. And if it's concave down, that lets me know that it is a maximum, okay, at this particular point. So we want to make sure that we've answered the question, and the question is, what dimensions should be used so that the enclosed area will be maximized? Well, we found our y value, so now to find the x value that goes with that, we're just going to plug that y value back into x equals 100 minus 3/2 y. Okay, so we can say x equals 100 minus 3/2 times the y value that we just found. So that was 100 over 3. Okay, so we get 100 minus 100 over 2, or 100 over 2 we know is 50, so we get 50. So our dimensions are going to be, for x, 50 feet by, for y, 100 over 3, or 33 1/3 feet. Okay, these are the dimensions that will give me the maximum area.